Problem 32. Here we have an example, one application to Gaussian to Gauss's law about a cylindrical shell. I take a conducting or metallic cylindrical shell of external radius 7 centimeter. You know that a cylindrical shell has two radius, internal and external. I give you the external shell equals 7 centimeter and length equal 2.7, has its charge uniformly distributed. So we have Q equals to, we don't have Q, we have Q as a charge. Let's draw the cylinder. Here we have the cylinder with an external radius equal 7 centimeter and with a length equals to 2.4. So here we have 7 centimeter and 2.4 meter. At the magnitude of the electric field at a point 19 centimeter radially outward from its axis. When I say outward, it means that the charge is positive. So at a point A, which is at a distance equals to 19 centimeter, the field is out. So here we have E. Okay, this field E of the point A equals to 36 K. K, it means 10 power 3 Newton per Coulomb. Find the net charge of the shell. Okay, now I have to find Q. Q is the charge distributed on the cylinder. Before starting the solution, let me explain the problem. Here we have a conducting cylindrical shell. In this case, the charge will be distributed on the external surface of the cylinder. Okay, so it will be at a distance 7 centimeter because it's a conducting, it's a metallic object. In the case of a uniform object, non-conducting material, in the case of a uniform object, the charge will be distributed uniformly inside the object at any point in the body of the object. Okay? But in this case, we have a conducting object. To calculate Q, you know that before we have the field at the point A. In general, in the case of a cylinder, if we want to calculate the field, we can use Gauss's law. And by symmetric, we use a cylinder of radius r as a Gaussian surface. Okay? We solved, or we have a video about this cylinder. How can we apply Gaussian surface in the case of a cylinder? So here we have to use a Gaussian surface by symmetric we take a cylinder of radius R as Gaussian surface. In this case, R equals to 19 centimeter. Okay, you know, A is a point on the surface. Okay, we have to write the conditions. First of all, dA, in this case, dA, I mean dA, it's the normal on the lateral side. Here we have dA. And it's the field. Here we have the field as a point A. Also, it's outward. We can say E is parallel to dA. It must be. Second, E must be radial. What I mean, if you prolong E, it will pass by the center of the cylinder. Okay. Third condition, E must be constant at any point on the surface of the body of Gaussian surface. After, we can apply Gauss's law. Flux equals the integral of a closed Gaussian surface, E dA equals to Q N divided by epsilon. You know, the first part relates concerns the Gaussian surface. The angle between E and dA equals to 0. So we can say here E dA cosine 0. It's important to write in details all the steps, equals to Qn divided by epsilon. Okay. Here, you know, E is constant. We can get out E from the integral. We have E integral dA equals to Qn divided by epsilon. So EA equals to Qn divided by epsilon. Okay. A is the area of Gaussian surface. A must be equal the perimeter of the ring times the height. So it's equal to 2 pi R times H equals 2. Okay. Qn, you know, here Qn in this case the charge will be distributed on the, not on all the body of the cylinder, just on the surface. In this case, Q must be equal sigma times A. Okay, sigma times A of the cylinder. Now I am talking about Q of the cylinder. Okay, the internal one. We can say Q, you can say A prime. And the external one has A. So Q is distributed on the, we have a surface charge density. If we have a uniform charge density, if this object is not metallic, in this case, we have to calculate the volume. We have to talk about the volume because the charge will be distributed inside all the body of the shell. But in this case, we have a metallic conducting or metallic object. So it's only on the surface. So we have a surface charge density. So here we can say because the object is a conducting cylinder, so the charge Q is distributed on the external surface of the cylinder. Here we have internal and here we have external. Okay, so we can say we have, in this case, we have a surface charge density. When we say we have a surface charge density, in this case, we can write Q in general equals to sigma times A prime. I'm talking about Q. Q is on the cylinder, okay? If you have a non-conducting material, if you have a material where the charge is uniformly distributed inside, it's not a metallic material, you have to say Q equals to rho times V, because you have a volume charge density. But in our case, we don't have, we have a conducting material. We have to say sigma A prime equals to, anyway, I want to calculate Q. We can put Q equal sigma A prime, or we can keep its value, Q. Okay, we can say Q like this. Here, in this case, Q in equals to Q. Why? If you see here on the body, you have the charge, Q. Here we have Q. This charge is located inside the Gaussian surface. So Qn equals the total charge Q. We can say, so we use this equation. We can say Qn, which is equal to Q, total Q, equals to E A times epsilon 0. Okay, Q equals to E equal 36 times 10 power 3 times A of the cylinder equal 2 pi r h, 2 pi equal 3.14, r equal 19. 19, it means 1.9 meter times h equal 2.4. This is E times A, epsilon 0, it's a constant. Let me give you the value of epsilon. Epsilon equals to 8.85 times 10 power minus 12. Okay, this is the value of Q. We get 9, 1, 2, 3.6 times 10 power minus 9 coulomb. Okay, this is a value of Q. This value equals to sigma A prime if you want to calculate another thing. Okay, now so we can see here this value equals to sigma times A prime. But me, I need just to calculate Q. Okay, thank you. Okay, I forgot part B. We have to calculate the electric field at a point 4 centimeter from the axis. Okay, here we have the axis and I want to calculate the field, let's say at the point B. Okay, at the point B, if we want to calculate the field, we have to apply Gauss's law. You know, we don't need to repeat the same equation of Gauss's law. By symmetric, we use a cylinder of, okay, we don't need, just we say, we apply phi equals to integral E dot dA and equals to Qn divided by epsilon. And we have to choose a Gauss's Gaussian surface. Okay, this surface pass by the point B, which is at a distance equals to 4 centimeter. You know, Qn inside the Gaussian surface equals to 0. We don't have any charge inside the Gaussian surface. We have nothing here because all the positive charges are distributed on the external surface. Here. Okay, we have nothing inside. Here we have nothing. So Qn equals to 0. We can say here the flux, which is equal to the integral E. We can say EdA. Okay, anyway, if you don't have Qn, you don't have E. Okay, EdA equals to 0, so E equals to 0 at the point B. Okay, this is the answer of part B.